Your pre-lesson, 7-3. The title is called The Discriminant. Now, I'm going to just show you right away what they're talking about. The discriminant is this strange part of the quadratic formula. Now, I'm going to come back to that in a little bit. We got to go over some basic terminology. So what you're going to notice on page 67 before we actually get into some sample problems are, upper right-hand corner, you're going to have to decide or discuss. This is more of a terminology lesson than it is math, but it's half math, half terminology. The first thing you're going to have to decide is your answer going to be real, a real number, or imaginary? That's going to be easy. Equal or not equal? That's got some strange stuff to it, but I'm going to do my best to explain it. And then you're going to have to decide, is your answer going to be rational or irrational? Now, there are some samples on your page there you can look at, but I'm going to try to simplify it a little more and just give you some basic things to kind of wrap your brain around. So first of all, let's talk about real versus imaginary. Like I said, this stuff is going to come from your discriminant. So in other words, as you plug things into the quadratic formula, you really only have to concentrate on this square root portion. Now, some teachers, that's all they concentrate on. I'm going to have you look at the big picture because when you actually find the answer, it'll be a little easier to understand the language behind it. So, with that being said, here's all your real numbers. 3 square root of 16, what does that equal? That equals 4. Square root of 19, what does that equal? I'm not sure. I could look it up on a calculator. I know the square root of 16 is 4. And I know the square root of 25 is 5, which is also a real number. So this has to be in between. I'll just take a guess and say 4.3. That could be a terrible guess. It could be decent. 2.1, that's a real number. The imaginary numbers are any square roots of negatives. Now, you may not know why you say this yet, but if you plug stuff into your quadratic formula and you get the square root of a negative, like these, your answer is going to be imaginary conjugates. That is all you can stop the problem there because you're going to have imaginary numbers and you're explaining that it's conjugates, which means you know that there's a plus or minus. Remember, conjugates are x plus 2 and x minus 2. There's a plus going on and a minus. That's where this language comes from. It comes from that plus or minus. So I don't want to ignore the whole quadratic formula, even though you can get your answer from that piece, which is called the discriminant. I know that's a lot of language, but it is simple at the end of the day after we talk about it a little bit. So let's move on to this. So what happens if I have a problem like this, and I say x plus 2, x minus 2 equals 0, I'd say, hey, my answers are negative 2 or 2. I mean, come on. Are these two answers equal? No. So I would say about my answers, those are not equal. I mean, that's pretty easy. So if you get two answers, 3 and 7, of course, they're not equal. A little trickier. What about these? Well, this is 4 plus the square root of 2 over 3 and 4 minus the square root of 2 over 3. Those are two answers hidden in the quadratic formula, but they are definitely not equal. Now, why do I have this trinomial sitting here? Let me throw an equals 0 here and let's solve it. So I'd go x plus 3, x plus 3. Remember, this is a perfect square trinomial. That's why it factors into the same two binomials. My answers, plural, are negative 3 or negative 3. Well, Captain Obvious says these two things are equal. Now, here's the twist, okay? If you take this information, and this is the most confusing thing, so please give me your undivided attention. If you take this stuff and you plug it into the quadratic formula, you're going to get negative b plus or minus the square root of b squared minus 4 times a times c all over 2a, which would be 2. Watch what happens. This is 36 minus 36, which is just 0. So this portion of the problem disappears. but you have the square root of 0. Keep that in mind, the square root of 0. So, which disappears. And I get -6 over 2. So a lot of students would think, oh, I only have one answer. See, that's the danger of the quadratic formula. If you have two answers and they're the same, and you plug them into the quadratic formula, it's only going to spit out one. And you need to just know, there's two because of that highest power. And so even though the quadratic formula would only spit out one answer, you'd say, aha, that's my trigger. Those two answers are equal. Another trick, whenever you get the square root of a 0, you know your two answers are going to be equal. A little confusing, but again, we're talking more about language than we are about math. And then the last thing to explain to you is the difference between a rational number and an irrational. Now, the root word for rational is ratio. What's ratio? That's another word for fraction. So, is this a fraction? Yes. Is this? Well, technically it is. 4 over 1. Square root of 16 is a rational number because that also equals 4. Irrational numbers are these. Square root of 11, 12, 13, 14, 15. In other words, non-perfect square roots. I know you guys are familiar with this little symbol, pi. Pi is 3.14. It is the most irrational number anyone has ever talked about because they can't find the end of the decimal. This actually equals 22/7, and this just goes on forever. And if you think about something being irrational, it's like, I just don't understand it. And so if you put that into that compartment, that should help. But basically, irrational numbers are square roots that aren't perfect. It's that simple, okay? Because I think if somebody really thought about 2/3 and you go, well, that's 0.66666666666, and that never ends, which is irrational, and that's where we'd get confused. Just remember this. Non-perfect square roots are irrational. Perfect square roots are rational. It's that simple. All right. With that being said, we're going to dive into some sample problems and see if we can't dig our way through this.